Hello. In previous video, we have just briefly introduced the linear algebra, right? So now in this video onwards, what we'll try to do is we will try to discuss about the vectors first. Then we will slowly move to matrices. We'll just try to get a very brief idea first. Then we will deep dive into other concepts. I hope hopefully you have seen the video I have shared from my other channel as well in this particular playlist. So vectors are basically the heart of the linear algebra, right? So everything, if you talk about in linear algebra, mostly it deals with the vectors and its operations over there, right? So understanding the basic understanding of vector is important over here. So that is what we will try to get it today. Then we will slowly move more complex stuff over there. So if I just talk about vectors, so if you have seen that particular video from my other channel, so if I just talk about vectors in terms of computer scientist perspective, so in that particular video we have seen certain example like this one, right, where we were actually talking about housing prices and based on like the different number of bedrooms, number of floors, area, right? So there for a single house we were basically depicting this particular informations, right? The number of bedrooms, floor, area and price as a vector, something like this one, right? Where the first element shows basically the number of bedrooms, the second element shows the number of floors, the third element shows the square feet and so on, correct? So and in programming's perspective, everything is an array over there, right? So whenever we talk about in terms of computer science, vectors we can think of as a container, like just like an array over there, right? Now if we just move to physics, so in physics vectors are treated differently. So let's say we want to depict this guy, force over here, correct? So now generally if you have already done the physics problems, so we generally show it something like this one, a directed arrow over there, right? So this arrow has couple of characteristics, like it has magnitude, it also has a direction over there. The current direction is in this way, right? So here in physics, so this is we call a vector, right? And we generally express those quantities where it has a particular magnitude as well as a direction over there, just like force or velocity, something like this one, right? And the portion where it starts, basically it's called the tail of the vector, and the portion where it has that arrow, basically it ends, is called the head of the vector, right? So the Latin meaning of vector is basically carries. That means vector actually shows us like what basically it carries from this point from tail to its head over there. So this is from the physics perspective. Now when we deals with mathematics, so it's basically a very generalized concept there. So it's basically talk about all the different concepts we have seen in computer science as well as physics as well. So it basically generalized this concept. So mathematically, if we just try to visualize vector or try to see what vector is, so first thing is we can think of vector as an element of a vector space. Now the question arises, then what is vector space? Now to be very crude way, if we can think vector space, it's a collection of vectors, correct? Okay, so where just like a community of vectors where each and every vector stays together but they follow certain rules. We will precisely basically discuss those rules in later videos, but for now we can just think of it's a collection of vector which follows certain rules over there, and the most important rules in that vector space should be the vectors could be added together or they could be multiplied by a scalar as well. In both of this operation we will get a vector back in the same vector space. Okay, so this is very interesting one. We will try to see a couple of examples, then it will be much more easier to understand. Okay, so let's forget about this particular sentence, and let's discuss, but we'll just try to add two things over here. Vectors are certain things which can be added together and which can be multiplied by a scalar over there, okay, for a very simple way. In later we will talk about more complex stuff, but for now let us try to start with this particular sentence, okay. So now let's see what it happens. So let's take an example of real numbers, okay. So we all know about this particular set over here, the set R, right, the set of real numbers. So now let's take a real number 2, let's take another real number 4. If we can just add this together, we will get 6, which is another real number, correct? Let's take another real number 3 and then multiply with 5, okay. That means, let's say either we are multiplying 5 with 3 or multiplying 3 with 5, does not make any difference, but we are doing a multiplication with a scalar, okay. And then we get 15, which is another real number over here. So that means real number also you can think of it as a vectors, because it's satisfying at least the two things we have started with. It can be added together, we'll get another thing which is part of this R as well. It can be multiplied by a scalar, we'll get another thing which is part of this R as well, okay. So real numbers we can think of it as a vector as well, and in fact it is a one-dimensional vector. Now let's move on. Let's talk about complex numbers. So, okay, so if you are not familiar with complex numbers, that's fine. Just we will see these things. Complex numbers are basically denoted by this particular letter C, capital C, complex number sets, right? Now why complex number has been discovered? Because we wanted to take square root of -1, right? So we wanted to get solution of x square equals to -1, that particular equation, right? So basically complex numbers we denote it something like x plus iy. So where x and y are the real number and the I is the imaginary unit, which basically equals to root over -1. Now if we don't know about complex number, that is fine, just take my word. So whenever we add two complex numbers, something like this one, so let's say x plus iy plus a plus ib here, we get something like this one, where we basically add the real parts together and add the imaginary parts together as well. So x plus a plus I into y plus b here. So we get another complex number if you see it here, correct? So which is part of this C as well. Now if we just multiply a complex number with a scalar, we will get something like this one. The scalar will be distributed here, something like this one. So Cx plus ICy here. Again, it's a complex number which is part of C. So complex number is also forms a vector space actually on the real numbers over here. So this also we can think of it as a vector, right? Even in fact the complex numbers can also be, in fact the complex numbers are also depicted something like this one as a ordered pair x and y, where this x plus iy you can express it as a x comma y, just like our coordinate system, right? We basically depict points over here in our two-dimensional coordinate system, right? So in our xy plane, correct? So but this for the complex number, this is in the complex plane over here. So complex number also we can think of it as vectors over here, and this particular notation is actually pushing us to the next level where we will be discussing about the coordinate space. So this is the most common vector space over here, right? And whatever you have seen in physics, like the way we depicts vectors over there, so all are part of this coordinate space over here, right? So let's take an example. So if I say I have a vector v which is 3 2 over here, so this is how mathematically we express vectors over here. Within parenthesis there are two numbers over here like stacked together. Either you can stack it as something like column wise in a single column, or you can stack it as a single row, So if it is a single column, it's a column vector, otherwise it's called a row vector over there. But what this particular number shows us, we will discuss later in this particular slide only. But let's take another vector called w, and it can be shown if I just add v plus w over here. So we will add the corresponding elements, first element of v with the first element of w, and the second element of v with the second element of w over here. So we will get something like 4 6. But let us try to visualize it pictorially over here. So this information, as I was showing in the complex number slide, so this information can be think of it as a point in our xy plane, correct? So let us do that. Let us have a xy plane over here. Now let us, if I just draw v over here, so what will be v? I need to go 3. If I just say the first element is the value of the x-axis, that means the portion I will go to on the x-axis, and the second one is for the y-axis over here. So if I just go on the right side 3, because it's a positive 3 on the x-axis, and if I just go up 2 on the y-axis, so I will reach this particular point over here, right? So this is the way, and if because I have started from the origin over here, that's why my vector tail is at the origin and my vector head is at this 3, 2 over here. Okay, and I am expressing it as a directed line over here. That is how we have expressed the force, velocity, those vectors as well, right? We'll very soon see an interesting fact over here as well. But for now, this is our v, right? Which is at the 3.3, 2 over here. Similarly, we can express w in similar way. So this is our, for v, this is our 3 and this is our 2. Now, if I just want to express w, so this is our w over here. So we went right side 1 from 0 to 1, and we went this one 4 from 1, we went up at 4 over here, right? So we reached this particular point over here. So this is our v and w. Now how we will express v plus w over here? Let us think about. But before we do that, we already applied this one over here, right? This particular rule where we were adding this corresponding elements here. So we got 4 6. So let us have this point over here as well. So this is 4 and this is 6 over here. So that means from origin, so this is our 4, correct? And this is our 6 over here. So that means from origin, if I just draw a line till this point, I will get v plus w over here, correct? So that means we actually added 2 vectors over here to get a new vector which is also on this xy plane as well, correct? So now if I just think very carefully over here in this case, we were always starting from origin over here, point 0, 0, right? Let's say if I just want to start from here and I want to draw this guy w over here. So how can I do that? Similar way, I will go to right side 1 because the first element is 1, and I will go up as 4. So if I just do something like this one, if I go right side 1 and if I go up 4, I will reach this point. That means this is my w over here actually, right? So now I get 2 interesting stuff over here. First thing is, if I place another vector, so basically if I place another vector which tail is actually coinciding with the head of the another vector, and then if I just add the tail of the first vector and with the head of the second vector, I will basically get their summation or the resultant vector over here. First interesting point. Second interesting point is, if we see it over here, this actually shows me if I just keep this direction and as well as this magnitude constant, I can move my vector any places over here, because here I was starting from origin, but in this case I was actually starting from this 3, 2 over here, this particular point, but it is still my same w over here, correct? So that means I can move these vectors anywhere in the plane, but I need to keep in mind that I need to keep its magnitude same and as well as its direction same as well. Okay, Similar way, I can move V as well, correct? From here, what I need to do is to draw a V, I need to go to 3 steps on the right side and 2 steps on the above side or the up side over here, correct? So this is nothing but the vector parallelogram law on vector addition over here. Now, as I said, the vector can be also expressed as a point as well in our xy plane over here, right? Similar with 3, 2 and w, 1, w is 1, 4 over here. Now let's move on. Let us see how we can achieve the multiplication with scalar. So similar stuff. So if I just take a v 2, 3 and w 0, 4, I have just taken a separate vector over here. So this is my w, right? And if I just multiply with 2, I will get 2w over here, correct? So this is nothing but our 2w, which is w plus w, which is 0, 8 over here, right? So we have just multiplied each and every element with 2 as well, if you see it. If I just think about geometrically this particular vector. Now similar way, if this is my v, I can multiply with minus 1. So what will happen? Both of these things will be becoming minus 2 and minus 3 over here. So basically it will be that its direction will be changing over here. If you see it, this is an interesting point as well. If you are multiplying with a positive number, the direction will not be getting changed over here. But if you are multiplying with a negative number, the direction will be changed as well over here, and it will be becoming a separate vector over here as well. Okay, even this is also a separate vector 2w, but anyway, but its direction is not changing over here. Okay, so if I just follow the same rule we discussed initially, we started with, so adding two vectors as well as multiplying with a scalar, also I'll get a separate vector which basically lies on the same plane over here, basically lies in the same vector space over here as well. Okay, so these are the examples of vector as well. Okay, and if you see it, like more we are discussing, we are trying to see is like how generic it is in mathematics, the vector definition over here. Let's move on. So if I just talk about higher dimensional space now, so I can have a vector something like this one, right, which have x, y and z component over here. So I can express p something like this one or this one over here as well. Okay, so with these things, if you see it over here, what we are trying to see it over here is we are actually moving to higher dimensions over here. We started with a very scalar value, correct, which I said a single dimension vector. Then we talked about two-dimensional vectors over here. Now in this particular one, we are actually seeing a three-dimensional vector over here. Now if I just think more generic way in modern mathematics, we can think of in higher dimensional vectors over here as well. It could be any number of dimensions over here. It could be very much hard to, actually impossible to visualize it beyond 3 dimension, but if we just talk about conceptually, those dimensional vectors exists, and we can see it, lot of theories as well on regarding that part as well, and we'll try to solve a lot of problems as well regarding that one. Okay, but if we just understand this smaller dimensional stuff, it will be very much easier to visualize it at the higher dimensional as well. Okay, so we talked about a very important and most discussed vector space called the coordinate space or Euclidean space over here, right? So now let's move on. So this coordinate space actually, as I was talking about, is actually generalizes to a n vector over here. That means a higher dimensional vector. We could have any number of elements, n number of elements over here. Okay, and each and every element is actually depicting me as a single separate dimensions over here, and it is nothing but Rn over here. Okay, so now if I just move on to take another example, now we are moving to something more. So we have a system of linear equation, which actually the fundamental question linear algebra started with, right? So a system of homogeneous linear equation also closely tied with a vector space. That means there is a vector involved over there as well. So let us see an example. So this particular equation over here, list of equation over here, if you see it, And if we just work on the solution of it, we will get something like this one. B equals to a by 2 and c equals to minus 5a by 2 over here. And if you see, it has multiple solutions over here, right? So this ABC is actually forms a vector over here, a vector space over here, if you see it, right? So we can actually depict this particular list of equation as Ax equals to 0, where A is my coefficient matrices. We still not talked about matrices. We will talk about very soon, but at least for now, let's go by my word, right? So A is my coefficient matrices and X is ABC over here, as I was talking about. So this is nothing but a vector over here as well. Okay. So basically a system of linear equation, we can express it in a single equation called Ax, where A is a matrix and X is a vector over here. Now let's move on. Let's take about another very interesting vector space called functions. Even functions, we can treat it as a vectors as well. So but it has to abide by those basic rules. Like if I add two functions, so for a particular domain, I would be getting another function over here. Okay, so for example, this one, e to the power x and e to the power minus x. So if I add this fx and gx, so we basically get the hyperbolic cos x over here. Let's take this one. Let's draw this one over here. So let's say here I will just say function plot, and here I'll just delete this guy. So let's first draw e to the power x, e to the power x. So I will be getting this one over here, right? Let's add a regular plot and let's try to draw e to the power minus x over here. So I will get this guy over here, right? So now if I just add it, regular plot, and if I just try to add these two guys over here, e to the power x plus e to the power minus x here, so I will be getting this orange line over here, right? Now I am saying it is 2 cos hx, right? So let's see that. If I say 2 cos hx here, so if you see, this magenta line is actually coinciding with this orange line over here as well. Okay, so by adding two functions, we basically got another function over here as well. So functions also we can thought of as a vectors. So if you see in mathematics, it's a very generic concept over here. Based on what vector space you are talking about, the nature of the vectors changes over there. Okay, so hopefully I did not confuse you. At least we got a very basic idea about where the concepts of vectors comes in mathematics, and we got a very brief idea about vector space, but we will talk more about this one as well. Now in next video, probably I will talk about similar kind of way about the matrices. Okay, then slowly we move on over there to the other concepts. So hopefully this video was helpful. See you in the next video.